While the ether functional group is quite stable under most reaction conditions, it does react with strong acids such as HBr and HI to cleave the ether linkage. When a non-cyclic ether is used with an excess of the acid, this results in splitting the ether into two alkyl halides through sequential protonation and then nucleophilic substitution events. The mechanism for this process involves iterative proton transfers and nucleophilic substitutions. The acid protonates the ether to generate a good leaving group, which is then displaced by the liberated halide anion acting as a nucleophile. Repeating this process on the thus formed alcohol gives the second alkyl halide product. In the first step, the powerful acid delivers a proton to the ether oxygen to give an alkoxonium ion. This now features a very good potential leaving group, and the released halide ion is now a potential nucleophile. The nucleophilic halide anion then attacks at carbon, in this case via the SN2 pathway. Attack at the less crowded primary carbon is faster to displace the alcohol leaving group. This affords the first equivalent of alkyl halide product. Since an excess of the acid is employed, the liberated alcohol will be protonated quickly to set up a good leaving group and a second halide nucleophile. The bromide anion then displaces water in a second substitution reaction to give the second equivalent of alkyl halide. In a similar reaction with a symmetrical ether, two equivalents of the same alkyl halide would be formed. In conclusion, ethers react with strong halide acids to produce alkyl halides through a sequence of proton transfers followed by nucleophilic substitution reactions. If an unsymmetrical ether is used, the less crowded side will react first and two different alkyl halides will be formed. For a symmetrical ether, two equivalents of the same alkyl halide are produced. For a cyclic ether starting material, a dihalide results featuring halide groups at both ends of the same chain.